Welcome back to the deep dive. For all you number theory students tuning in, we're continuing our exploration of the OEIS, the Online Encyclopedia of Integer Sequences. Such a fantastic resource.
Absolutely essential, I'd say.
Today we're tackling, well, a really interesting one, A000319. It's got this description, tangent iteration.
And it's a perfect showcase, really, of how complexity can just sort of emerge from seemingly simple rules. It really challenges intuition.
Yeah, definitely. So our plan is to unpack its definition, look at how it behaves, which is quite something, and touch on some fascinating open questions surrounding it.
Sounds good. It's a great sequence for illustrating unpredictability in elementary math.
So let's lay it out. The core definition, AN is the floor of BN. Okay.
Right. And Bn comes from iterating the tangent function. So Bn is tan, Bn 1.
And you have to start somewhere, so B0 is set to 1. That's the initial condition.
Exactly. So you start with 1, take the tangent of that result, and so on.
And that floor function you mentioned, that's crucial, right? Because tan gives you real numbers, but we want an integer sequence.
Precisely. It just takes the integer part, discards the rest. But the tangent function itself, well, it behaves quite wildly near its asymptotes.
Yeah, I was thinking about this. So iterating it and then taking the floor, what kind of sequence does that produce? Is it predictable at all?
Well, let's trace the first few steps.
Yeah.
B0 is 1.
Okay.
B1 is tan 1, which is about 1.557.
Right, so A0 would be floor tan 1, which is 1. Wait, no, A0 comes from B0.
Oh, B1.
Oh, the definition is AN floor BN, so A0 floor B0 floor.
Careful there. The sequence starts at N0 in the OEIS definition often, but sometimes implied N1. Let's assume AN depends on BN. So B0, B1 tan on approx 1.557, so A1.
Then B2 is tan B1, so tan approx 1.557.
Which is about 74.68, quite a jump. So A2 becomes 74.
Wow, okay. Big jump. What's next? B3.
D3 is tan B2, so tan approx 74.68. And that value, well, it plummets down to roughly Menniket 0.8635.
Minus. So A3 is floor, 1 task 0.8635, which is minus 1.
Exactly. So you go from 74 to -1 in just one step. That huge oscillation that's really characteristic of this sequence.
And that immediately signals, I imagine, huge computational headaches.
Oh, absolutely. It's incredibly sensitive. A tiny, tiny change in an early beginning value may be due to rounding.
That gets magnified massively by the next tangent calculation.
Catastrophically amplified, yes. You need immense precision. The sources mention using 3,000-digit precision.
3,000 digits, just to calculate terms.
Yes, and even techniques like interval arithmetic, where you track a range of possibilities instead of a single value.
Right, to try and bound the error and be sure you're getting the right integer from the floor function.
Exactly, because if your computed value is super close to an integer, say 74.99999, or 7500000, a tiny error flips the floor value completely.
And even with all that, they've only computed, what was it, a couple million terms?
Just over 2 million last I checked, which sounds like a lot, but given the effort per term, it highlights the challenge.
It really does.
Yeah.
It makes you question how we even know a term for sure, way out in the sequence.
That's a deep point. The very nature of computation versus, the true mathematical value. Interval arithmetic helps, but the sensitivity is fundamental.
Okay, so given this chaos, this oscillation, and the difficulty, what about the actual values that appear? Does anything strange happen there?
Well, that leads directly to one of the big open questions. Does the number 319 ever actually appear in the sequence AN?
319. Why that number specifically?
It's just, well, it hasn't shown up in the first 2 million or so terms computed. And it's notorious for not appearing in related sequences, too.
Really? Like which ones?
Sequences A053169 and A053873 in the OEIS. They have similar iterative definitions, different starting points maybe, but they also seem to avoid 319.
Huh. So it's like this little numerical mystery. Is E3A19 somehow forbidden by the dynamics of these tangent iterations?
Or is it just incredibly rare, needing us to compute vastly more terms? We don't know. It's possible there's some structure, some forbidden zone created by the tangent iteration and floor function that 319 just can't land in, or maybe it's just hiding.
Fascinating. Okay, so to wrap this up, we've looked at A000319, defined by AN, floor, BN, where BN, BN-1, and B01.
We saw its wild oscillations and the extreme computational difficulty due to the tangent sensitivity.
Right, needing massive precision and things like interval arithmetic just to be sure of the terms. And we landed on this specific puzzle. Does 319 ever appear? a question tying it to other sequences as well.
Indeed, and it leaves you with this thought, doesn't it? You have this simple-looking rule, iterate tan, take the floor, basic operations, really.
Yeah.
Yet it generates this incredibly complex, unpredictable behavior that challenges even powerful computers. It makes you wonder what other secrets, what other unexpected patterns or missing numbers are hiding in sequences like this. How much is really going on just beneath the surface of simple iterations?
A really provocative question. It certainly challenges our intuition about number patterns and where complexity comes from. Something for you, the listener, to ponder.